Hello, hello. We're going to present to you first little unit on nuclear physics. Basically, what this is going to cover is isotopes, three types of radioactive decay, and nuclear fission, nuclear fusion, and a little bit of the technology like nuclear power. And let's go ahead and start reviewing a little bit about isotopes because we learned about atoms in chemistry last year. So there's going to start with some early models of the atom. Now, the model of the atom in the days of Isaac Newton, which a lot of our physics revolves around, was a tiny, hard, indestructible sphere. He would have called it corpuscle. But back in 1897, J.J. Thomson was looking at how the electron would fit into a model of the atom. So you might remember Thomson's model being called a plum pudding, or kind of looks like a chocolate chip cookie. Thomson's model are embedded all together in a mass or a spherical volume, surrounded by positive charges, kind of like the electrons would be seeds in a watermelon, okay? It was Rutherford who later came along, and he proved that there's no way Thomson's model could be correct. Now, Rutherford did the gold foil experiment. In the gold foil experiment, he fired a beam of positively charged particles against the thin metal foil. Rutherford concluded that all of the positive charge is probably in the center or like the middle region, right? And there's a bunch of empty space. And then he called this region sort of in the middle where most of the atom's mass is, where the positive charges are, the nucleus. So any electrons would have been farther away outside the nucleus. So Rutherford thought that the electrons, because they're not in the nucleus, must have been revolving or orbiting around the nucleus. But if they really were orbiting around with the centripetal force and electromagnetic waves giving off energy, eventually the atom would fall apart pretty quickly. So there has to be some other reason why the electrons stay, quote unquote, in orbits or stay far away from the nucleus. So it wasn't until Niels Bohr, I hope I said that right, proposed a new model of the hydrogen atom. And he explained atomic spectra. This is where we get into the quanta. Remember, quanta was a mathematical model of the atom. So in Bohr's model, only certain orbits are allowed. And the electron is actually never found between these orbits. So like a ladder has different rungs. It would be like you could only put your feet on the rung, right? They would never be in between. But when the electrons change orbits, they quote unquote jump instantaneously from one orbit to another. So the idea here is that electrons have certain areas where they are predicted to occupy. And in order for them to move from a different zone or area, or we can call it an orbit if we like, they have to have some kind of energy given or taken away. So let's quickly talk about what the properties of a nucleus is. It wasn't until more recent times that a nucleus was just thought to have nucleons, that is, protons and neutrons being similar particles in that area of the nucleus. So we did look at last year in chemistry mass number. So let's talk about these nuclear quantities, nuclear being pertaining to the nucleus. The mass number represents all of the protons and all of the neutrons. These are what would be referred to as the nucleons in the nucleus. So all particles in the nucleus are represented by the mass number. It's the total proton plus the total neutron. And the atomic number strictly represents the number of protons in the nucleus. And then the neutron number represents the number of neutrons specifically in the nucleus. But look how we annotate our chemical symbol. Here's aluminum, for example. We write the element, and to the left up and to the left upper is the mass number, and to the left lower is the atomic number. This is a way that we can commonly identify the element and write its numbers. So what makes an isotope? Well, atomic number really gives you the identity of the element, right? The atomic number doesn't change with the element. The atoms of the same element can have different mass numbers, okay? This is because the number of neutrons in each particular element can vary. Remember how we would look at their periodic table and have those long numbers with the decimal after them, all right? Even those were averages. So atoms that have the same atomic number or the same identity, but have different neutron numbers and different mass numbers are called isotopes. So an isotope varies in how many neutrons the atom has. The atom's going to have the same amount of protons, but different neutrons. And this will be our last little slide for today. So when you look on the periodic table, you'll notice atomic mass is rarely a whole number. So it has all those decimal points after it. That's because we look at the average. Atomic mass is the average mass of all the isotopes of that element. So if you look at the atomic mass of carbon, it's 12.001. That's the average of all the types of carbon isotopes. It's the average atomic mass. Again, what's an isotope then? So an isotope is an element of an atom that has the same number of protons, but different number of neutrons. So protons and neutrons both in the nucleus, protons being positively charged, neutrons being neutral, collectively known as nucleons. And it is really the protons that give an element its identity, and neutrons can be isotopes of the same element. So if you have different neutrons. All right, I'm going to stop right here and we'll pick up the rest in class.